picking up a book, if you will, moving maybe a piece of chalk, okay, just rotating, doing in-hand reorientation. Some of these things look a lot like what we've come to expect RL to help us do, but sample-based planning can do them too with the right dynamically aware heuristics. But I want to think, it's actually interesting to me to see many of you are using trajectory optimization in your project. A relatively common refrain, like this week, maybe this is about the week where people are like, I've got my problem set up, but it doesn't find a good solution. What do I do, right? The first thing you do is you look at the debugging mathematical program tutorial because there's lots of hints about how to see which constraints are infeasible and plot intermediate results and all these other things, okay? But nonlinear trajectory optimization is fundamentally a local method and will be susceptible to local minima. It's not guaranteed to find a path if it exists. So you have to make sure your problem is formulated correctly, and there's debugging tools for that. But at some point, giving it a better initial guess is kind of the only fundamental way to make trajectory optimization work very well. So in this work and in other work, a lot of people will take, let's say, sample-based motion planning, which gives you potentially fairly random trajectories, okay, to find an initial guess. It's a little bit harder to put optimization directly into the sampling-based planners, but they can be enough to find an initial feasible guess, which you could then hand to a trajectory optimization. And in general, I didn't talk about it, but when you go to execute sampling-based motion planning plans, you almost always do some sort of smoothing after to post-process them, right? To make that you don't want to run the original trajectory that comes directly out of the random planner typically. Okay, so that's kind of where we've arrived with this motion planning world, is we've got trajectory optimization. It's really good at dynamic constraints, but it suffers local minima. We've got sample-based planning, where it's great for solving global problems, but you have to work pretty hard to put the dynamics in. Okay, and so what I want to talk about today, and what the goal of today is to try to understand sort of how we can put the two together. There are ways to use optimization that take a slightly more global perspective, that are less susceptible to local minima or not susceptible to local minima. But it's like the last chapter of our motion planning tools. This is something that's active research right now. So I'm going to go back and forth between on the board, and I have a little bit more than normal, some slides that I like to talk to. So, okay, I'm going to use a very simple example to talk about this. This is my airplane flying left and right around the tree, but even more simple, I'll just think about a point robot that needs to plan a trajectory around a single obstacle. Okay, this is my start. This is my goal. And this is my obstacle. Okay, I'm going to make it a box because that makes my equations even really easy when I write them down in a few minutes. And the reason that this, I think, highlights that discussion a little bit is because there really are two parts of the problem here. There's sort of a discrete set of decisions that you have to make in many of these motion planning problems. In this case, it's trivial, but you have to decide if you're going to go left or right around the tree. It can be combinatorial if you have a forest, for instance, and you have to suddenly decide left or right around the first tree, left or right around the second tree, or in every possible permutation. Okay, so we get quickly the discrete part of the optimization comes into contact with combinatorial optimization algorithms. And I'll give you the basic tool of that today. Okay, but the other part, of course, is the smooth optimization over curves. Once you decide I'm going to go right around, then I have to think about my dynamics and think about shortest path and think about, smooth curves and things like that. Okay, so different versions of the problem can sort of push on different aspects. This problem looks intimidating from a trajectory optimization perspective, but if I were to make it like, if I think about this as a graph search perspective, then it's sort of not a very scary graph search problem. Okay. If I want to fly a quadrotor through the maze, then I'm somehow bringing together the discrete problem of searching through the maze, but also a bunch of continuous constraints about what a quadrotor, the dynamic constraints of a quadrotor. So that would be kind of a goal for today, is to see if we can figure out how to make quadrotors, things with dynamics, fly through puzzles. Okay. All right, and again, just to say the same thing, but we have the combinatorial world where sample-based planning is the tool of choice right now. When we have combinatorial puzzles, the standard approach and the real way that this is addressing the combinatorial challenge is just by picking samples. And at some point, you'll pick samples from all the possible permutations, and then you'll do a graph search, which is solving the discrete, potentially combinatorial problem very efficiently. And that's in contrast with sort of the smooth trajectory optimization, which is doing good things on these kind of robots. Okay, so the things we've been working on in lab in the last few years are giving this kind of a result. Okay, so this is now a quadrotor in MeshCat flying through. You can come up with random sort of environments, and we have the dynamic constraints of the quadrotor, but we can solve to global optimality within some class of curves, okay, the trajectory optimization problems. So it's solving both the path around through the, should I go through the window, should I fly through the door? Okay, that's also taking into account the dynamic constraints of the quadrotor. The other cool thing is it works for manipulation too, so for manipulation style planning. So these are just complicated collision-free motion planning problems where you would think trajectory optimization might struggle with local minima. This is like, it's got to pick up a mug over here. This arm has to pick up a mug over there. That's not a very good angle, Russ. Let's try that again. Okay, but these arms are kind of playing Twister, if you will. And but it's able to solve the trajectory optimization. So I haven't given you any tools from trajectory optimization that would solve that problem yet. Here's just the real robot doing that kind of thing. Okay, so let's think about, back in this very simple example, what's the difference between these kind of trajectory optimizations that we're doing here versus the ones we've already talked about? Is that setup sort of clear? Yeah? Okay. Let's just first write what the non-convex, the original trajectory optimization would look like here. I'll do a dumbed down version of it, and then we'll adapt it into the more global version, okay? So, let's say I'm gonna have a bunch of decision variables. So I've got x0, x1, x2, and I'll imply that they'll be the breakpoints in my, or the knot points in my curve. Okay. All the way up to xn. Okay. So I could write a trajectory optimization problem that's saying I'm going to minimize over x0 to xn. Maybe if I want some surrogate for a shortest path, I can write that as a. I could just take the distance. Distance squared happens to be slightly better for this problem for some reasons, but again, you should do that. Okay, so that would be somehow just penalizing the squared distance between each of these points. The reason it's subtly better to do the squared in this problem is because then it encourages the points to spread out evenly. Okay, if you just had distance, then there would be no reason no reason for them to be spread out evenly. Okay, and then I can add my initial condition constraint, something like I begin at the start, and at the goal. And then the interesting thing is, how do I encode the obstacle, right? So we talked about the minimum distance constraint before, but let me just keep it simple and keep it at the origin. All right, and I'll say it's a box of, it'll just be the L1 ball, okay? So just the unit ball, the absolute value norm, so I just write that as, for all n, I'll say that xn in the L1 ball has to be greater than or equal to 1. Okay. So this is the collision avoidance constraint, right? And it's a non-convex constraint. If less than or equal to 1 would be a convex constraint, but being outside this convex region is a non-convex constraint. And fundamentally, that's at the heart of these obstacle avoidance problems. Even if you have convex obstacles, being outside them forces you to then make a decision about left or right. Okay, we can of course put this in code and play with it. Okay, the way I've written it, there's actually no reason why it wouldn't clip the corner, but you can do a little bit more work to make it not clip the corner, right? The constraint's a little bit stronger, but I just said all of the points are outside the region, okay? And I've given myself a little GUI here so I can actually just move the start and the goal around, and I'll have it, so when you're solving trajectory optimizations in sequence, you can often use the previous solve to start the next solve. That's called warm starting your solver. Okay, and that's a standard thing to do in real-time trajectory optimization. Okay, but if I warm start the solver, then it exposes my local minimum problem, right? Because I can move this around, it does beautifully good things, but when I move it over here and I start, if I move the goal over there too, it's clearly stuck in the local minimum. There's obviously a shorter path, but it's not gonna find it. It's never gonna find it. And why is it never gonna find it? Is because in order to move to the other side, it has to get worse before it gets better, right? It has to violate a constraint, right? And so any gradient-based optimization is not gonna find that. All right, so how do we make trajectory optimization a little bit more global? The standard first combinatorial optimization tool that we put to task in these problems is mixed integer optimization. So let's write the same problem just a little bit differently. Okay, I'll write the simple version first, and then we'll back up and explain what mixed integer as a class of problems is. Okay, so what if I instead wrote the constraint that just says I'm outside this space? Okay, so I can write the same exact decision variables. If I wanted to say my points are outside of that particular face, then I could write that as this is the vector 1, 1 in this case, right? So I could just write this as 1, 1 times x is greater than or equal to 1. Okay, that would say I'm outside of this space. But if I only pick things that are outside that face, that's clearly not going to get me all the way from the start to the goal. Okay, so I also have to say, no, maybe I'm outside this space. Or maybe I'm outside this space. Maybe I'm outside this space. So I could write this as a disjunctive constraint. I say or, that would be down this side here, or 1, -1 x greater than or equal to 1, or 1, -1 x less than or equal to -1. Okay, if I can write that, if I can transcribe that into an optimization problem, then that would certainly capture saying that every one of those points is outside the object, right? These are called disjunctive constraints. They're certainly non-convex constraints, but there happen to be a particular type of non-convex. We know how to write these particular non-convex constraints in a way that we can use combinatorial optimization tools to address them. Okay,
methods just to show you that I can do this first. Go to my next thing here. Okay, this solves the problem nicely. Okay, if I can solve that problem on every time step, even with a warm start, in fact, it doesn't even need a warm start in this case, it's going to solve that to global optimality. Okay, the question then becomes, how do you actually write that disjunctive constraint from an optimizer? And the trick is that there's this class of problems called mixed integer optimization. So back to the slide here. Okay, so mixed integer programs are optimization problems like we've looked at, where you have some objective function. Oh yeah, sure, go ahead.
Sorry, I think I missed. So as you define the disjunctive constraints,
Yeah.
it's already enough to do what you just showed, or?
Yeah.
So what about it? What is the system not ability?
So, okay, good question. So what about it? So, basically we have stronger solvers for this problem that will solve a disjunctive constraint of a particular form. These are a disjunction of convex constraints. And where I previously used gradient methods to solve it, and I couldn't do better, this is a class of problems that has a convex objective and convex disjunctive constraints, and I can solve this one to global optimality. Good, thank you for making me say that, I forgot to say that. Okay, so what is this class of problems that we have some slightly stronger solvers for? I have an objective, F, I have constraints, X, but I'm going to partition my decision variables into the continuous variables, X, like I normally always had. Then I'll label some of my variables B, just to make them clear. This is mixed binary, the way I've written it, okay? Where the binary variables are restricted to be 0 or 1, okay? That or right there is exactly the or that gives us the power that we need to do disjunctive constraints. And the solver can think about, you could imagine writing a solver for this. A very bad solver for this would be to try every single possible value, every combinatorial problem choice of B. I'll try all zeros, I'll try all ones, and I'll just go through and try them all. And each one of those is a convex problem, so I know I can get a global solution to that problem. Yeah, sorry, if in the case it's mixed integer convex if F and G are convex. Okay, in that setting, we should expect to have better solutions. What's amazing is that if you're in this mixed integer convex setting, you can actually have very efficient algorithms for solving these problems. Okay, that using convex relaxations, right? So if I were to take that B, 0 or 1, and change it into B between 0 and 1. Then that problem can be seen as a relaxation of the original problem. It's only easier, so it tells me something about the original problem, right? In the best cases, it can be that if you relax the problem and you just solve this problem, then the solution has the property that B is either 0 on one side or it's 1. Like if all of your B's, after solving that convex problem, happen to be 0 or 1, you're done, and you know you have the global optimal solution. More commonly, B will end up between 0 and 1, and then you do more work to try to make them. But you can imagine if the B's in the convex solve came out to be like 0.9, another one came out to be 0.1, that's a pretty good indication that of how to move along the sort of search tree. Yes?
Can you give some intuition for what convex means in that, in the disjoint case?
The total problem is not convex. It's only if our other constraints are purely convex. Okay, so I'll give you like the simplest encoding of a disjunctive constraint would be, it's not necessarily the best one. Would be using, let's say, you might have heard of the big M notation. So if I wanted to write, for instance, say I have C1 x less than or equal to D1, or
C2x less than or equal to B2. Something like this. Then you could say, well, let's do it, yeah, I'll start with this one, I guess, okay. So, then I could write this with a big M notation as C1 of x less than or equal to D1 plus B times M, where B is a new decision variable, I'll call it B1 here. M is just a big constant that I choose a priori. Okay, I'll say C2x less than or equal to D2 plus B2 M. These are the same things. Okay, I say that all of my B's are 0 or 1. And then in this case I'd say at least one of my B's has to be 1. Okay, so what's the intuition of that? I have a constraint, x has got to be less than or equal to D1. Okay, but I'm going to take that upper bound, and I'm going to put a big number next to it with the binaries. So if the binary becomes is 1, then the upper bound effectively moves far away. So it's trivially satisfied, that first one, and it effectively turns off the constraint. Right, if I just wrote C1 of x less than or equal to infinity, then that constraint is just turned off, it's gone. And in practice, you pick an M that's much less than infinity, but much bigger than your other problem variables, and it just pushes that upper bound out of the way. Okay, and you have another one for B, and then this just says that at least one of them has to be on. Yeah?
For some intuition for how the convex relaxation works or when it's tight, so is it maybe reasonable to say, oh, instead of, we consider B's instead of on the corners of some hypercube, like the entire space of the hypercube, and what it means for convex relaxation to be tight is that we will always land on one of the corners anyway.
Yes, that's very, so a good property to have would be if your convex relaxation is tight. I agree with you, this is just a hypercube, the B's, if I relax it to the interior of the hypercube. So you can imagine if you have a linear objective in the hypercube pushing out of the inside, then you will end up in the corner, right? If you start adding additional costs and constraints, then you can mess that up. The game becomes how do you write good optimizations that succeed in getting to the corners of that hypercube. Yeah. Yes?
So if the B is 1, the constraint is off, you said?
In this case, if B is 1, the constraint is off. Did I write that backwards then?
Yeah.
So I should say that at least B should be less than or equal to 1, I guess, in this case. Yeah. Good catch. Good catch. Okay, so let's take this, the simple version of the disjunctive constraint that I did, and let's look at its convex relaxation, right? So we saw it solves to global optimality. It's still solving the global optimality. I'll let that going. Okay, and I'll just run exactly the same example with the convex relaxation instead, solving that instead of the original problem, okay? It's not great. It basically learns nothing about the problem because it's effectively it's saying I'm either here or here. Yeah, and it's taking the convex hull of them effectively, okay? So we've known for a long time how to write mixed integer optimizations of trajectory optimization, but they have traditionally performed very badly because the convex relaxation is not very tight. So I can stop this one. Okay, so how do we solve this more efficiently than just brute force search? And why does the convex relaxation being tight matter? Okay, it's this branch and bound algorithm you might have heard of, branch and bound, okay? The idea is you first just solve the convex relaxation, okay? And let's say you came up with integer, the binaries came out to be 0.9 and 0.4. Okay, now you're gonna start a search process. Well, you'll have some heuristics. This one, probably most heuristics would say that I should branch on B0 first because it's close to 1. Okay? But I still need to run potentially 2 optimizations. I'll check if I were to say B1 equals 1 as a constraint, a linear constraint, and then just solve the rest of it as a convex relaxation. Or I can solve with B equal to 0 and solve the rest of the convex relaxation. Okay, then I can just sort of go through a tree and set each of the individual variables to either 1 or 0, and that gives me a search tree. The important thing is that because the convex relaxation is only easier than the original problem, it's a lower bound on the total cost. Okay, so I have some hard constraints to satisfy, 0 or 1. I relax that into 0, between 0 and 1. So I made the problem easier, I might get a lower cost. Okay? If I find a solution that has binary variables that may or may not be optimal, it gives me an upper bound. If I can find any solution that's binary feasible, that gives me an upper bound. So the name of the game in branch and bound is that I can rule out entire search trees. Okay? If I know something about by solving this convex relaxation, that the lower bound is 3, okay? But I say over here that the upper bound is 2.5, then I never have to traverse that entire tree. So even though there's a combinatorial search waiting for you, you can discard massive parts of the search space just by using these bounds, by keeping track of these bounds. That's the key idea in branch and bound. And you can sort of see why the tighter the relaxation, right, the faster you'll discard all of the other candidates. In the best case, you can just know immediately if your upper bound and your lower bound are equal on the first solve, then you're done. You don't even have to traverse the tree. That's when the convex relaxation is tight. You can see your integer feasible. Okay, so the way that the performance of these things scales, and they've so how many people know Tomás Lozano Perez in ECS, right? It used to be that I would say mixed integer linear programming or something to him, and he would do it. Okay, yeah, Turing complete, I don't care. And, it's like a worthless algorithm because it's so general that you can code anything in it. It's not going to give me anything useful for robots. And that's a fair, it is potentially combinatorially bad, right? It scales that way with the number of integer variables. That's going to set the size of my search tree, right? And the tightness of the convex relaxation is going to affect the performance. And unfortunately, in the motion planning transcription, like the simple one I gave you here, where we use disjunctive constraints to say left or right around the obstacles, that has traditionally given both too many integer variables and very loose relaxations that go right up the middle. Okay, so why do I say false combinatorial complexity here? Right, so in this optimization, I put a binary variable for every decision xn, right? So it's like I'm independently deciding for this cell whether I was going to go left or right around the tree, and separately, as if I had no other connection, I'm going to solve for this one. So I've got this combinatorial complexity that grows with the length of my trajectory, when intuitively there really is one decision to make. Right? So I've added false combinatorial complexity to that problem. The other thing I don't like about these formulations is just the fact that you have to pick n beforehand. I've always disliked that. It's like, why should I have to pick 41? Remember you guys called me on the 41 in one of my examples before? That's annoying. It's not just a modeling nuisance, but I think it makes the optimization landscape worse. Right? If the solution is different for 40 and 41, then somehow there's something a little bit funny in the problem. And traditionally, people haven't thought of these as super effective planners. So we've been working with Pablo Perillo, and I mentioned him a number of times, but he's a close collaborator with us. And I was complaining one day about how these, we know how to write these, especially planning through contact as mixed integer optimizations, but our relaxations are so loose and the solvers take forever. It's just something's wrong. And he called me on it. He said, we know how to solve shortest paths on a graph, using optimization, and the convex realization is tight. So what exactly did you do to break your formulations, right? And so we spent like the last 3 or 4 years now trying to answer that question to satisfy Pablo and the like, and we've now got much better optimization algorithms. Okay, so I want to tell you this LP formulation of the combinatorial optimization that solves the graph problem. Okay, so if I have a traditional shortest path, imagine I've got this graph here, so this is just a directed graph with a number of vertices V, okay, directed edges E. I've got a source S and a target T. My path, I could put weights on the different edges, and the goal is just to find the shortest path, weighted shortest path from start to the goal. Of course, we can solve that with dynamic programming. We can solve that with Dijkstra's algorithm. There's lots of different graph search algorithms that we can use, but we can also solve it with convex optimization. Right? That one you might have not seen. The way it goes is if I say that my costs on my edges are just my costs L, let's say. So if I say let's minimize over some binaries B. Okay, I'm going to use Bij equals 1 if the edge from vertex I to J is in the shortest path. Okay, and then this is just the edge cost. So this cost tells me the length of the path, of the shortest path. And it's going to sum all of the edges that are in the path and just add up their costs. Okay? Now I need to make it I need to make this a consistent path. Okay? So the way I'll do that is, for instance, to say J in EI out. Hold a second. Okay, this is the flow constraints. It says that at every edge, or every vertex, the number of constraints of edges that are coming in must equal the number of edges going out. It's a linear constraint. We have a special case for the source and the target because they don't have any in on the source, so I'll leave that out, but I would just put a delta function in there to capture those. That's just a clever way of writing a linear constraint which captures, we'd only expect the sum to ever be 1 or 0, okay, but it's a clever way to capture the fact that it could be 1 or 0. Basically, if it's on, the sum on the way in has to be 1, and that means the sum on the way out has to be 1. Okay, if I add plus some of the Bij at the source equals 1, target equals 1. Right, I can add a special case for the source and the target. And then, of course, I want to have Bij 0 or 1. That's a mixed integer. This is a linear objective, a linear constraint. So this is a mixed integer linear program. MLP. MILP. It's a famous class of problems. A lot of you'll hear people talking about MILPs, for linear programs. Okay. But this is a special one. This is one that we know that the convex relaxation is tight. Okay, so you can, with a little bit of work, you can actually prove that the optimal solution to this, of the linear program, always has the objective is always pointing to one of the vertices. And in fact, if I relax this to 0, between 0 and 1, I will get an integer feasible solution. In fact, in this particular problem, all you need, you can actually relax this to bij greater than or equal to 0, and that's enough. The 1 is implied by the other constraints. Okay, so the way that we're gonna do better, we're gonna take this idea and bring it back to the planning around obstacles idea, is with just a simple sort of extension of that, which we're calling search on a graph of convex sets, okay? So the modeling is that you're gonna still do a shortest path through a graph, but every time you pick, you visit a node, a vertex in the graph, you're allowed to pick one element out of a convex set. So in the planning problem we're talking about here, I'm gonna have regions that are like, I can choose various ways to put regions, but I'm gonna break down my space into various regions, okay? Just like I did the left or right above, let's 1, 2, 3, 4 regions, okay? And I'm gonna say, I'm gonna find a path. I can make an additional one for my source, additional one for my target. Okay, and I just need to find a path that visits this, and then visits this, and then visits this, for instance, right? Or it could take this path around. That's much closer to writing the true combinatorial complexity of the problem, okay? And it becomes a graph search where you're visiting some convex set. You're allowed to have edge costs that are functions of the continuous variables, okay? In this case, this is the blue regions are the things you're visiting, not the obstacles, okay? So I take this shortest path problem, and right there, this is the case, this is the way you would typically write it that includes the source and the target. Just have these Dirac deltas to handle those special cases. And you can write almost the same optimization problem, but you're gonna now include these continuous variables x, right? These constraints are almost the same. We're gonna add a few more constraints to it in the next slide, but even if you just were to solve this to global optimality, you'd already be in good shape, okay? The constant edge length cost times the binaries has become the function, the convex function edge length cost times the binaries. Otherwise, it would basically the same. Yes?
So it's not anymore though like a linear thing that you're doing, it's.
Say it again?
We're gonna be minimizing something that's like quadratic or convex, right? Not necessarily linear.
That's a great question. So this looks like a non-convex objective. What are we gonna do with it, right? So the first, we have to, so I'm gonna say that Lij is convex function, but if I multiply by another decision variable, it looks like it's not convex. But it's, we can write convex forms of that. So the convex set, or a convex function, convex set is the easier word to think about, times a non-negative scalar is still a convex set. So it becomes the perspective, they call it, of that convex set. Okay, so we can still actually treat that as a nice way, because we know we know that B is non-negative. Okay, so the non-negative scaling of the convex set is still a convex set. Yeah, you can think about the picture you can have in your head here for sets, but it works the same. You move the objective to a constraint. So I've got some convex set. I've got the origin here, and so the perspective function takes non-negative scalings of that convex set, and this is still a convex set. Okay. So some things, when I say everything bilinear is immediately non-convex, there's slightly more subtle than that. Just doing that already made things like dramatically better for branch amount. Just leaning on the linear programming sort of solution, putting binaries on the edges instead of saying individually that every point needs to be in some set. That made a huge difference. But Tobia, who's the main student who was working on this, the first version of this graphs with convex sets stuff, he would present every week and to talk about what's working, what's not working. And we had all these like simple graphs, simple motion planning kind of problems, or simple graphic kind of sets problems. And we would find cases where the relaxation was perfectly tight and cases where they weren't, where it wasn't tight. We have proofs that say it can't always be tight for every graphic convex set. Okay, but there were some instances of that problem where the bound that was being solved by the linear program was not, so Pablo, it was really interesting the way he would think about this. He'd say like, you are never smarter than a linear program. You know, if you have intuition that there's a lower bound, like the straight line path or something, or if there's any intuition that you can sort of puzzle in your head that is better than what you're getting out of your linear programming solution, then you probably missed something. You probably wrote the wrong linear program. Okay, so we kept sending Tobia back to the drawing board, and he found there's a really important idea in optimization, especially when you're in a game of relaxations, which is that you might want to add additional constraints, which don't change the outcome of the original problem. Like if I solved the mixed integer binary problem, then I can add constraints that wouldn't change that solution, but they might tighten the relaxation. Okay, so we're thinking about what are additional implied constraints that if we knew the binary variables were 0 or 1, we could add these in and they wouldn't change the solution. So one of those is if you take the conservation of flow constraint and you say that take the decision variables associated with the vertices, if the decision variables associated with the vertices sort of have to go to 0 when the binaries turn them off, then that's an additional constraint on the continuous variables that's implied by the graph. When this is solved to integer feasibility, it's exactly implied by the original constraints. But in the intermediate, where you're in the convex relaxation, this adds additional power. Okay? So this is what we call the spatial conservation of flow. And what's important, the reason I took it to highlight, this is like an explicit connection now between the continuous parts of the optimization and the discrete parts. Right, so the continuous constraint, we can put constant constraints on X, we can put our dynamic constraints of our vehicle or other things, okay, that are gonna change the discrete part, even in the convex relaxation, and the discrete search is gonna change the continuous variables. This was the most important missing constraint. After that, many of our optimizations started to really work well. Let me go slightly out of order because I wanted to. So this is now the basic recipe for some of the demos I showed you at the beginning. Think about the sampling-based motion planning picture. Okay, so you've got obstacles, but instead of making a graph with vertices and having no room for like dynamic trajectory optimization because you just have straight line edges, what we're gonna do instead is every time we sample a point at random, we're gonna grow a region, a convex set, and then we're gonna connect these as graph of convex sets on top of that sample-based solution. Okay, so the picture is going to change from the original PRM kind of picture into something that looks more like this, where the black is the obstacles, the yellow are the regions you're allowed to go in. And then we're going to put decision variables in the continuous sets that'll define curves. And compared to the PRM solution, where there's sort of no room to satisfy dynamic constraints or optimize smoothness or anything like that, now we've given ourselves big convex regions to optimize curves over. And we can solve graphs of convex sets, optimization problems, in order to get nice, more global trajectory optimization. Yeah?
But why can stay with points? Because there are good algorithms for tessellating spaces, for instance.
Good. So in smaller problems, so the question is why don't we just explicitly sort of tessellate the space? And so in low dimensions, we have good ways to decompose the space, especially if polygonal geometries, we can just do exhaustive tessellation, and that actually is the way that we have polynomial proofs for Euclidean shortest path in these small problems, but it doesn't scale to like really big problems. So and more complicated collision geometries and the like. So if we have a 17-dimensional or 14-dimensional space of our EWAs, and we're trying to, move around in there, then we have to give up total coverage. We do approximate, this is just a class of approximate convex decompositions. Good question. Okay, so if we're careful about the way we do that approximate convex decomposition and we make those regions carefully, then we can actually say some things that are stronger. You know, I kind of intentionally left that optimization to clip the corner before, and it happens in sample-based planning a lot. You know, even if you sample densely, you can miss intercollisions. Okay, we have the opportunity here to potentially put constraints on and say that we're guaranteed. We might not be complete, there might be a path that would have required me to cover this in my approximate decomposition. Okay, but in this case, we'll be guaranteed collision free, and then within the class of curves that we parameterize that decide these sets and polynomials up to some degree, we're actually going to be globally optimal. If you solve the branch and bound, okay? But the sequel, of course, is that it turns out you almost never have to solve the branch and bound because it's so tight that you just solve the convex relaxation. Okay. Yeah, so I just talked about that. Any other questions at that level? Yeah.
It seems like now the large part of the problem is the tessellating.
Yeah.
Is that-
Well, it's not. I'd say they're both hard still.
It seems like once you get the constraints right, that you solve the relaxation, you get the right answer. But it's hard for the computer.
Yes.
It's hard to write, but it seems like it.
No, that's
seems to kind of solve.
That's a great observation. Right? So maybe we just move the hardness into the pre-processing, right? Which is to come up with these regions. I think that's part of what's happening. But I'll show you there's good algorithms for that too. Yeah. I think we're separating the hardness into two pieces that we can solve.
So before the spatial conservation of flow constraint, then even if you didn't visit a set, the decision variables, the continuous decision variables there might be non-zero. Is that right?
That is true. Is there anything else that would have caused them to be zero? Certainly not in the version I wrote before. We had a few other constraints flying around that could have turned them off. But I think that happens to be true. But I think more importantly, this is just something that puts more pressure on X, even when the binaries are not 0 or 1. Right? That even if binary is 0.5, for instance, it still asks for two different X's to have, you optimize the cost, whatever. It puts extra constraint directly on that. Okay, so now we're into a problem where, for these kind of problems, we can actually write, the closer to the true combinatorial complexity. Right, we're going to just enumerate decompose the different regions, and the reason I get around having to pick n, the number of samples. First of all, I know that a straight line path in a convex set is going to be collision free, so I don't have to enumerate lots of points to get that property and check them all. And second of all, the length of the path even in the simple shortest path problem, the number of edges in the path is not. There's no upper bound on that based on the number of decision variables. Well, there's a number of edges, of course, but you don't have to pick a priori how long the path is. That comes out of the optimization. To me, that's a huge win. RRT, you never have to pick how long the path is in an RRT, but in trajectory optimization, you always did. Okay. Of course, I'll have to run that. So this is just a sanity check. Of course, it needs to solve the problem that the other mixed integer solve did. But the cool thing is that's the convex relaxation. Okay. I can turn it on or turn it off. Yeah, see, the convex relaxation was actually true during all that. That's a super simple instance, but it's surprisingly true for much bigger instances. Yeah?
Are you have tools to make this easier for other problems?
Yeah. So we have the graph of convex sets machinery, which is just general. You can put traveling salesman problems in there. You can do all kinds of stuff. And we have a class, graphic convex sets, which just helps you add convex sets and then solve that optimization. And then on top of that, there's a motion planning with graphic convex sets that does curves and collision geometries and stuff. So those are separated. Yeah. Cool. It's surprisingly effective, right? So we take back this original problem, and let's say we actually want to have continuous curves, so we want to solve like shortest path or shortest minimum time or something like this, but we have some dynamic constraints. We want the curves to be smooth, we have to have smooth continuous derivatives. You can find paths like this, right? And that's just a convex relaxation, right? Which is, again, like from the graph perspective, that's not a hard problem. From the trajectory optimization perspective, that's a terrible problem. But I really like this because I've never really thought of that as like something I would get out of a convex optimization, But the of course, it's written in a different space, right? So it's convex in this other space, but it gives in our Euclidean space that picture.
So you just have a bunch of little boxes that are like tessellated in space? Or?
Yeah, so we just break up. This one we didn't have to do anything approximate, of course, we just made the exact boxes for this. And we have, continuous curves fitting in all those boxes. And if we tried to write that with the original mixed integer formulation, it would just not, you wouldn't even try. This would be too big of an instance, it runs out of memory just even putting it into the solver. Yeah, so there's all these connections to Euclidean shortest path. It's a well-known, well-studied problem. We haven't said P equals NP or anything like that. In low dimensions, you can do exact decompositions. There's polynomial time algorithms that leverage those decompositions. Okay, well, all we're saying is that we have now a polynomial time algorithm that works in higher dimensions, and it's often tight. If it was always tight, then P equals NP, and that's not. And we know that it's actually we can take we can reduce the Hamiltonian path problem into this problem, so we know it's actually NP hard. But it solves this more general class of problems. You can add dynamic constraints. So for instance, think about LQR, okay? I can write LQR, finite horizon LQR, as a GCS problem. Be a particularly boring one in some sense, but imagine I just have a bunch of sets all in a sequence, okay? And I have my decision variables X here, right? And then I could just put constraints. I didn't say explicitly that you can write convex constraints, but if you can add convex costs, we can also add convex constraints on the edges. Then you just basically write your so you'll actually make the sets that have both X and U in here. And then you just constrain that the X here has to equal my dynamics, right, times the previous X. And I make a graph that's the horizon length, and I can solve the LQR problem. You wouldn't do that, you can solve the Riccati equation, you wouldn't need graphic convex sets for that. But you can do, once you have this observation, then you can do more interesting things like, remember the problem that we couldn't quite solve before, which was minimum time LQR, right? We didn't know what the horizon length n was. Okay, now we want to discover like what's the right length of the path. Then I could have like a goal region over here, and I could have potential transitions from all of the different sets, okay? And graphic convex sets machinery could choose to go for a variable number of steps before just transitioning to the goal. So it can solve a richer version of that problem. Moreover, you could have different dynamics in the different cells, right? And because of that, this is actually an effective way to solve the piecewise affine quadratic regulator. Which is like LQR, but now it's PWAQR. which is a pretty effective, modeling for, for systems with contact, for instance, yeah.
Do you use it for walking? This seems like a good way to get out of having a fixed gate schedule.
That's exactly the kind of thing, that's exactly what started these conversations. So we're gonna have you, we're hoping to have a problem for you to do graphic convex sets for footstep planning, because it fits nicely into that. Yeah, and then, we are absolutely doing it for planning for contact and stuff like that. That's exactly one of the big motivations initially. So this was like, in fact, that was one of the mixed integer problems that we had thought about most in the group were footstep planning problems, like we used in the humanoids. And the first thing we tried was trying the new formulation compared to all the old formulations for mixed integer footstep planning. Cool, okay, so does kind of make sense that something happened with, where we gave the solver the ability to think about logical, discrete elements with these integer variables. The integer variables were the connection to the continuous variables. Right? Once we write mixed integer convex things, we can blend discrete logic with continuous logic. We've got new vocabulary of things that we know how to solve well. And if you write, the graphic convex set is just an effective transcription. It uses a small number of integer variables and tends to have tight relaxations. Okay, so maybe I'll show you how we put all those together and how far we've gotten with it so far. So the smooth curves, it looks like this. So if I have to move around my red obstacle, then we make this convex decomposition of the free space. And then for every one of those regions, we put a piecewise polynomial. There's particular classes of piecewise polynomials that are effective for this. So we use Bezier curves, which are parameterized by by some number of control points, and have this nice property that we know that the continuous curve is always inside the convex hull of the control points. So that way we can guarantee that if the control points are in the region, then the curve is guaranteed to be in the region. You can also do things like put constraints on the derivatives of the derivative of a Bezier curve is also a Bezier curve, so you can work on it. You can put the same sort of convex hull constraints on derivatives, any higher derivatives, okay? And then we make this discrete graph just by when two regions touch. If they have a non-zero, if they have any intersection whatsoever, we make a bidirectional connection in the graph. And then at optimality, so we add constraints to those edges saying that if the edge is on, then the points must be continuous and must have some continuity to some degree. Separately, because we want to think about the dynamics, we also have a time rescaling. So we don't know, if we separate out, just to make things fit into the convex optimization framework, we separate out the path of the curve from the timing of the curve. And we have actually sort of two curves in every region. Just like I stuck U in as the decision variables here, we stick a time rescaling in the decision variables in these problems. So then you can optimize things like the duration of the path, or the path length, or the path energy. And you can have collision avoidance, not just with the samples, but at all times. You can put velocity constraints. These are like the modeling power of that. And you can solve them with different objectives and get very different solutions, but we're solving the global optimality. Right, so it's a transcription of the motion planning problem to mixed integer convex, and it happens to have a very tight convex relaxation. So if you want to solve the global optimality, you can do that with branch and bound, and it's way faster than before. But you also can only solve the convex relaxation, the first step of the branch and bound, and almost always get the optimal solution. Yes?
Smooth in those piecewise sections, how do you deal with them being smooth and like continuous in the derivatives when you connect them?
Exactly right. So since the Bezier curve is the derivative of the Bezier curve is also a Bezier curve, then if you just have the control points of the derivative curves are in the same point, that means the derivatives of the two curves have to be the same at that. And you can recurse and do that at higher degrees. When you combine the time scaling, that's where we have velocity continuity, but we don't actually have acceleration continuity, because it becomes non-convex there. Yeah?
What does that do to the dynamics if you're rescaling in time?
Right, so the trick becomes how do you write convex dynamic constraints on, in that sort of a formulation. So in the quadrotor example, we leverage differential flatness, which I think you're gonna have a problem about. It's definitely written up in the notes. I thought about talking a lot about it. We said, this is a problem set kind of thing. So you'll see that actually paths of the center of mass of the quadrotor, because there's dynamic limits, there's only one dynamically feasible way to execute those paths. So you can actually just think about the paths of the quadrotor and get dynamically feasible trajectories out. Okay, but you can also do this kind of dynamical unrolling too, and try to put dynamic constraints on the edges or on the continuous curves. And the name of the game becomes, what's the tightest convex approximation of the dynamic constraints that reduces the envelope of possible curves. Okay, so like in that quadrotor example, so I said that it's almost always tight, and it's kind of interesting to think about what, how do you can't prove that it's always tight. We know that we have counterexamples, can't always be tight. But we just made a bunch of random instances of quadrotor environments, and we ran both the mixed integer version and the convex relaxation, and we just asked how often do they get the same answer? How often do they get the right answer, right? And so like almost always in these environments. And then there's a different question you could ask, which is, if you only solve the convex relaxation, you don't even try to solve it, because that's the whole point is that you don't want to solve the hard one, right? If you look at just the convex relaxation, that gives you a lower bound. If you then take any of the things that are not quite 0 or 1 and round them to the closest one, there's a correct way to do the rounding, then that gives you a feasible solution, that is an upper bound. If those are the same, then without solving anything more, you know that you're at the optimal solution. If your upper bound and your lower bound meet, you're done. Okay? So the question is, how often, with only solving the one problem, do we know that we're optimal? We're actually optimal this many times, but only 45% of the time do we actually know that we're optimal right out of the gate. And in general, we are a little bit unsure of ourselves, but we never think we're really bad. The gap is small.
So certified in this context just means you round. Is that what happens when you round and then you figure out what you're optimal?
Yeah, the certified optimality gap is the gap between the upper bound and the lower bound compared to the true objective. Yeah. Okay, so the hard question, Sam, was how'd you get those regions, but I'll answer that in a second.
In a normal application like that drone example, 25% non-optimal, is that ever a problem?
I think no. It takes a longer path. Actually, the thing is, it almost never takes a longer path. It just doesn't know it's it's not sure with only the one solved that it couldn't take a better path. Right. And in general, so this is actually a really important point. I like tools from global optimization. That is not because I like global optimality or I quest for global optimality. I think that is, always there's like weirdness in our model. Our dynamic model's a little wrong. Our constraints are a little wrong. Trying to be globally optimal is kind of not. It's a fool's errand in some sense. But what I want is something that gets around local minimum, that thinks about the entire problem structure and picks, finds the path when it exists, and smooth paths, and thinks about dynamics when it's trying to find a path. Right? So even if the gap was bigger, I would be okay. Yeah.
Are these algorithms fast enough to run real time?
Okay. I have a slide for that in a few minutes, but yes, I think they're fast. So the pre-processing is slower. There's two ways to do the pre-processing. The pre-processing can be slower, but in an environment where you're like moving the robot the same way all day long, then this is money, I think. So the actual optimization is fast, and the pre-processing is like minutes for the bilingual kind of stuff. Okay, so we have approximate convex decomposition algorithms that basically try to find, that some of you did this in manipulation and thought about this particular algorithm, right? We try to find big convex regions by solving these optimization problems that give us big interiors. And doing that in configuration space was hard, but turns out it's a good problem for sums of squares. Guess I'm predictable. Yeah, so we have like sums of squares, oh, should take that off, but sums of squares optimization formulations, where you're basically taking two complicated robots. I said the geometry, even the kinematics of our robots are polynomial, right? They look like they have sines and cosines, but you can always write sine squared plus cosine squared equals 1. And the same thing I said about doing sums of squares for reasons of attraction for robots works for sines and squares for geometry reasoning, okay? And we try to find certificates that say, as a function of the joint angles, find me a separating hyperplane that proves that two collision bodies are guaranteed to be collision free. So we need the geometry to be convex or decomposed into a convex set in the original space. In the configuration space, it's completely weird, right? The pictures I'm showing there, you just take Iwa, okay? And in the configuration space, it's this totally weird shape of like the joint angles that bring it into collision are the red spaces, okay? But we find big collision-free regions using these algorithms. And they're guaranteed, the sums of squares version is guaranteed. We also have a nonlinear optimization that's faster but not guaranteed to be collision-free. And it's like surprisingly tight. If you find the convex decomposition, even though there's like curved regions that we're trying to brush up against, we find that it tends to be very, very tight. So this is it's hard to visualize a convex region in joint space, 7-degree of freedom arm, but this is considering the configurations of the arm not trying to collide with the shelf or the mug, and we're just sort of walking around one of these regions, and what's important is that it's not shy about getting right up and close to the true geometry. It's really carving out a big part of that region. And it's also big enough to leave us nice room for the big continuous curve optimization. Yeah. So then we did a bunch of comparisons against PRMs with shortcutting, graphic convex sets, and to the speed question, in this one arm case, we're certainly competitive with PRM. We certainly find shorter paths. That's kind of by definition. And we tend to find them as fast or faster than the PRMs. Some people have worked more than I have on PRM optimization, but I mean, in our optimization, this is fairly optimized, and in our optimization, it's a lot better. So, and these are like milliseconds, right? So it's pretty fast. Some cases it's trivially fast. If we have some algorithms that look at the graph and try to rule out possible paths, if it can reduce the graph to like there's only one straight line path there, then it just becomes a linear program, but boom, it just solves it really fast. So there's cases where it'll just solve it very fast. We have versions of it that try to handle geometry constraints, like working on manifolds. This in particular, if the robot needs to possibly wrap around in 2 pi. Oh, that's not right. Okay, you can sort of do the right thing and never go the wrong way around 2 pi. Okay, and that's actually Tommy, who's normally here, works on that. And we do piecewise affine systems. We plan through contact a little bit. This is work in progress. So this is actually the thing we're working towards, is trying to reproduce some of the examples that people use in manipulation research for like pushing planar objects around. You can see there's a goal region written on the table there. Trying to push that in. This was a human teleoperated thing that was cloned into a neural network policy. Right, we're trying to do it with graphs of convex sets, where we have to make the tightest possible convex approximation of the contact dynamics in each set, and it's starting to work. So we'll see. So we're working on hard these days. This is actually inspired by a problem that Alberto Rodriguez had been working on, and actually Orion Taylor is going to give a thesis defense about that in the next days. Where he's got real robots that are pushing and working through the sliding regime and the like, and so we have versions of that are working now with these convex relaxations. Cool. I mean, there's a lot more I be happy to say about it, but that's the main message for today, right? Is that there's sort of three classes, I think, of planning problems: the trajectory optimization, the sample-based planners, and then these that try to bring them together. And I think these are the youngest ones, but I'm excited about them.
What are other good methods in this third class?
Yeah, I mean, I think, so people have done, so John Howe, for instance, was one of the first to write down the mixed integer linear program for flying around obstacles. So that's a known, you know, I think sometimes used, it's very expensive based on the number of obstacles. So in the motion planning world, I would say we are still very, we haven't used all the best tools for combinatorial optimization. If you ask me what are the tools for combinatorial optimization, then there's many more tools than that, but I think the roboticists haven't found them all yet. In fact, someone was saying, we're gonna organize a workshop on global optimization for robotics. And we'd love to have you come and give a talk. I said, that's great. Yeah, they said, do you know anybody else that works on global optimization? And they're like, we can't find anybody, you know, so it's not a big thing. Yeah. Yes?
Are you ever trying to say anything about your solution compared to how high the resolution is of the convex regions?
Okay. You're saying so define resolution for me then, so.
I guess like when you're doing these sort of like convex region approximations,
Yes.
how far you go, or, yeah.
So I want to think about this as the convex decomposition as a big swath of continuous space that's not discretized at all. It's just a continuous thing. I have discretization inside it, which is based on the degree of the curve that I put inside it. So I can pick polynomial bases of a certain degree, for instance. So there's some limits, there's some sort of discretization or resolution limit in that. Okay, and then there's, I think the other one you're referring to is just covering the space. I could try to cover it with like big regions, lots of small regions. It's hard for, we don't know exactly what makes the best cover for this kind of algorithm yet. We tend to think we want big regions that overlap a little bit. The example of that's an NP-hard instance is actually a case where all of the sets overlap, and you can walk around and have to visit every single set in order to find the optimal path visits every possible set. That's the Hamiltonian path problem. So we try to, just because we have one instance of that that's really bad, we try to avoid that in practice, but I think we're still learning exactly what's the right way to cover the space. We could think about, in the same way that the PRM is probabilistically complete, or the RRT is probabilistically complete, by eventually we'll sample every nook and cranny. We could do the same thing here, where we eventually try to sample every nook and cranny and have some convex set that covers that. So in terms of completeness, we think about it that way. Yeah, I'm sorry, yeah.
It seems that while we're no longer choosing the sort of control points that are defining our trajectories, that's sort of being implicitly encoded in the graph structure, but that is being sort of given by the convex approximate decomposition. So does that almost feel like you're trying to come up with an algorithmic answer to this question, almost, of how many points to use in like the approximate version?
Yeah, I mean, let me make sure I get your point right. So, in every region we have to pick a fixed number of bases for our polynomial. Okay, so I do have an n in there, but the number of regions that I visit from the start to the goal is undetermined. So that's the thing I like, is that the length could grow, the number of decision points could grow or not. So in what sense do you call that an algorithmic?
Well, because a priori you need to give those regions to the algorithm to solve, and that is something that, I mean, Iris does really well, but in some way something that Iris chose for you.
Yeah, I think that's fair. Yeah, we're certainly not doing more than the. I mean, you could say that about the graph search too, right? So I have to give it a graph. So there's certainly some total number of vertices in the graph, right? But the path length in the graph, I don't know a priori, and I don't have to specify. I feel the same way about Iris. So I think that's an important thing, is to be able to not have to know the length of the path in the graph, and that's all. We're not doing anything more than that here.
Maybe it's like sort of like a reduction of user degrees of freedom, maybe. So we sort of maybe re-centered on maybe the natural
I see, okay. Yeah, it's partly better for the user, I think it's also better for the optimizer. Right, the same way, remember how, like, I had to pick 41 and 42, like, didn't quite work at 40, right? That weirdness is an actual problem, and I think getting rid of it helps you solve better, harder problems. Good, keep asking questions about your projects. I mean, I'll always stick around for a few minutes afterwards, and, yes, please ask questions, and good luck, yeah.